What is going on, guys? Welcome back. In this video today we're going to learn how to do parallel computing using CUDA, which is Nvidia's parallel computing platform and toolkit. So let us get right into it. Alright, so CUDA is, as I already mentioned, Nvidia's parallel computing platform, and it is super important in machine learning because in machine learning, a lot of the tasks are actually just linear algebra, matrix multiplications, matrix operations, vector operations, things like that. And CUDA is optimized for exactly that. And in this video today, I want to show you how it works. I want to give you a very simple introduction example of a parallelized hello world, which is not very useful, but you can see how it basically works. And then we're going to implement something more advanced, which is a matrix vector multiplication, first in Core C and then in CUDA to see the performance difference there. Now, to get started, what you need to have CUDA and the CUDA toolkit installed on your system. The easiest way to do that is to just follow the instructions here in the documentation. So you have instructions for Linux, you have instructions for Windows, and probably also for Mac. You will hopefully find all three of them in the description down below, so you can just follow the installation here. I think though on Linux it's quite simple, at least if you have the basic Nvidia drivers installed. And of course you need to have an Nvidia GPU for that. You cannot do this with an AMD GPU. But I think if I just run this command here, I should be able to see where I'm running the compiler from. Yeah, Nvidia CUDA toolkit. So this is what you have to install, but if you want to make sure everything works correctly, just follow the installation instructions here. Now, I need to mention that this video is going to be quite advanced in terms of it requires you to already have some C knowledge. It requires you to already know basic programming concepts. So this is not an introduction video for someone who has never coded in C, never coded in C++ or anything like that. If you only know Python, you can still watch this to get some inspiration to see how it works, but don't expect to understand everything here because I'm going to just use concepts or apply concepts like malloc, so allocation of memory, freeing memory and stuff like that, without explaining how it works and why it needs to be done. So once you have everything set up, we're going to go into the directory that we're going to be working in today. So in my case, it's this one. It says Python, even though it's not going to be Python today. And we're going to start with a basic Hello World example. So CUDA is basically just C or C++ code, but it's actually CUDA code. So it's very similar. The language is almost the same, but you have some additional functions and data types and stuff like that. And we're going to start now by creating a file called hello_CUDA.c, but we're not going to create a C file, we're going to create a CU file. A CU file is essentially a CUDA file instead of a just core C file. And here now we're going to start by writing an ordinary Hello World program in C, but then we're going to change it so that it can be parallelized with CUDA. So we're going to start by include, and then we're going to include stdio.h, and then we're going to define a function hello world, and this function will just printf hello world, or actually wanted to say hello CUDA, so let's call this hello CUDA \n for a line break, and that is basically the function. Then we have our main function here, which takes some parameters, maybe argc, and then also argv, and then we have the return 0 at the end, and then we call our function hello CUDA, and that is basically our C program. Now, what we can do now in CUDA, or maybe let me show you that this actually works in C for those of you who are not so familiar with C. Move this to this, and now I can just compile it. And the ordinary way to compile a C program is to say gcc, or whatever compiler you want to use, hello CUDA, and then hello CUDA is the output, and then I can just run hello CUDA. So this is an ordinary C program now. Now let's move it back to a CUDA file. Let's go into it and change the code so that it can be parallelized. And what we're going to do here is we're going to make this void function here, we're going to make it a global function. So global underscore underscore global underscore underscore void hello CUDA. And then when we call this function, we're going to actually specify 3 angle brackets, opening and closing. And in here, we're going to specify the grid shape and the block shape. The basic idea of CUDA is that you have multiple blocks that are aligned in a grid, and then you have in those blocks multiple threads. Now, maybe I can give you again a not so good visualization here. I'm only going to use my mouse, so this is not going to look too great, but you have basically a grid in your GPU, you can say, and in this grid you have different blocks. So we can maybe split this up. If this is now 2 by 2, so we have this 2 by 2 grid. We have block 0, 0. We have block 0, 1. We have block 1, 0. And we have block 1, 1. Now, those blocks themselves contain threads. So these different blocks are again split up here. Maybe we should use a different color for this. They have a structure themselves. So maybe the block itself is also a 2 by 2 block. Every single block is a 2 by 2 block. And in those blocks, we have now the thread 0, 0, and then 0, 1, and 1, 0, and 1, 1. And we have the same everywhere. So 0, 0, 0, 1, 1, 0, 1, 1. In all these blocks, we have threads. And they can have whatever shape you want. Now, I'm going to explain why this is useful later on. For now, it's not really useful. For now, it's just something that we need to know. And I'm going to now specify that I want to have 1 block and 1 thread in this block. So this would be 1, 1. And what we can do now is we can compile this, but we can compile this with the Nvidia compiler. So with the CUDA compiler, nvcc hello CUDA.cu, and then we can say output hello CUDA. And now when I run this, we will see everything is, oh, actually I forgot something important. To actually see the output, we need to call a function which is CUDA device synchronize to actually get the output here as well. Because otherwise everything is happening on the device. So we compile again, we run again, and we can see hello CUDA here. So that's quite simple. Now I can also say I want to have 2 blocks with 1 thread each. This would also work, but then you can see what happens is I run this 2 times. And I can then change this again, and I can say I want to have, basically, I can say either 2 blocks and 1 thread. I can also say 1 block with 2 threads. The result would be the same in this case. I can also say I want to have 2 blocks and 2 threads. So in this case, I would get 4 times hello CUDA. That's the basic idea of how this works. Now, why is this important? Why is this useful? We can access inside of this function here certain values, and I'm going to print them here for you so that you can see how this works. We can have a block index x, which is going to be a number. We can have a block index y, which is also going to be a number. We can have a thread index x, which is also going to be a number, and we can have a thread index y, obviously, which is again also going to be a number. And let's add a \n here. We can just get these values by accessing block idx.x, block idx.y, thread idx.x, and thread idx.y. And those are important because basically what we can do now is we can compile, we can run, and due to the shape that I provided, we only have x values because I said I want to have 2 blocks, and I didn't say I want to have 2 times 2 blocks with 2 times 2 threads. I just have 2 blocks, 2 threads. So we're only using the x-axis, but you can see that every time the GPU runs the code, it runs it on a certain block and on a certain thread. So we have block 0, thread 1, block 0, thread 0, and so on and so forth, which means that if I can say certain blocks of the GPU are responsible for certain blocks of a matrix calculation, this is very compatible because a matrix has a certain shape, a certain grid shape, and the GPU has a certain grid shape. And then I can just parallelize the operations in this grid shape sort of way. So this is what we're going to do now with a matrix vector multiplication. And we're going to start by implementing this matrix vector multiplication in Core C so that you can follow the thought process if you're not familiar with CUDA. And then we're going to do the same thing in CUDA so that we can see what changes and we can see also why it is faster. So I'm going to start here a new file, which is going to be matrix_vector.c. And this file here, what we're going to do is we're going to import, so we're going to include stdio.h. By the way, excuse my slow typing. I'm still getting used to my new keyboard. I changed the layout, so I'm typing a little bit slower than usual. But we import these two libraries here, and then we say void matrix vector product, let's say. And what we want to get here as an input is we want to have, first of all, a float pointer to a matrix A. We want to have a float pointer to a matrix V, to a vector V1, and to a vector V2, and want to have the matrix size, which is going to be an integer. The basic idea is that we're going to have an n by n matrix, an n-sized vector. We're going to multiply the two, and we're going to store the result in an n-sized vector, vector 2. Again, I'm not going to explain basic matrix vector multiplication. I'm not going to explain what a pointer is. I expect you to either know that or to not care about it if you watch this video. So we're going to define this function now, and we're going to do it in a very simple way. We're going to have a loop int I from 0, I being less than the matrix size, and then I plus plus. So we're basically just going through the rows. So we're going through row 0, 1, 2, 3, and so on. And in there, what we want to do is we want to keep track of a sum, which starts at 0, and then we're going to go through the columns. Int j equals 0, j less than matrix size. We can do this again here because we have an n by n matrix, so the matrix size is going to be the size of the row, or the amount of rows and the amount of columns, and then j plus plus. And all we want to do now basically is we want to say sum plus equals, and we want to add whatever the value, or we want to multiply whatever the value is at the current position. So we take I, the current row, but we take it times the matrix size because we want to go through the, so basically if you're at the second row, you want to not just go with 2, you want to go with, because we don't have a multi-dimensional array here, we have a long array, we have the flattened version of the matrix basically. And because of that, we don't want to just go to row 2, we want to go to row 2, but this means going 2 times the matrix size plus whatever position we're at column-wise. So I times matrix size plus j. So basically, maybe I can sketch this for those of you who cannot really follow. We basically have, why can I not draw now? Let me try again. Okay, now it works. Basically what we have is we have a matrix. Let's say we have a 3 by 3 matrix now. And what I have in C is not the 3 by 3 matrix. I have a 9, an array of size 9 basically. So we have 9 positions here, whatever. And what I want to do is I want to go to I being 0, I being 1, I being 2. But I being 2 basically means going 6 and then also whatever I need. So I have to go 6 positions to basically pass the first 2 rows. That's the reason why we do that. So I times matrix size plus j, how many, which column in that row. We take this value and we multiply it by vector 1 and then just the position there. And then in the end, what we do is we say v2 at the respective row is going to be equal to the sum. That is the result for this particular row. This is just a basic matrix multiplication, matrix vector multiplication. Then we are going to have our main function, which is going to take an int argc, character argv. Actually, we are not using that, but I'm just going to put it there. And then we're going to return 0 in the end. And what we want to do now is we want to just define everything. So we want to set everything up. We want to have a float pointer a float pointer v1 and v2. Then we want to define a matrix size. Now we're going to start with a matrix size of 3, just so we can see that the calculation is accurate. And then we're going to go with 40,000, which is a good value, I figured, to show the performance difference between this version and the CUDA version. So matrix size is going to be 3. We're going to say A. The matrix is going to be typecasted here to a float pointer. We're going to allocate, so we're going to use malloc to allocate the matrix size times the matrix size, because we have an n by n matrix. So matrix size times the size of whatever a float is on the system. So we can copy this. We can do the same thing with v1, v2. But this time, of course, we're going to just use one matrix size, because the vector size is going to be the same size as the matrix, but it's not going to be multidimensional. So if we have a 10 by 10 matrix, we're going to have a 10-sized vector. That's the basic idea. So matrix size times float size, and then we're just going to initialize our matrix and our vector with some basic values. So we're going to say for int I equals 0, I being less than matrix size, and then I plus plus. Inside of this, we're going to run a second loop. Maybe I can just copy this one here. But it's going to have j. And basically the idea is, let me open my paint again. What we want to do here is we want to, if we have the matrix like this, I mean, this is now, let's do it like this, 3 by 3. It's not the most beautiful matrix. We want to have just 0, 1, 2, 3, 4, and so on, whatever the size is. And for the vector that we're going to use, we want to have also 0, 1, 2, 3, and so on. That's the basic idea of what we want to do here for the initialization. You can also just use random initialization, but I didn't want to deal with the whole randomness in C now, because you have to come up with some seed that is random and stuff like that. But we're going to just do it like that now. We're going to say matrix A, I times matrix size again. So we just do the same thing that I explained above. So matrix size plus j, and the value of this is going to be exactly float, and then basically what's inside of the brackets. So I times matrix size plus j. So the position is going to be also the value. And then for the vector, we're going to do a similar thing. I'm going to copy this here. I'm going to paste it here. We're going to just say vector1 position I is going to be equal to float typecasting of I. And that is the same idea. Then we perform the matrix vector product. For this, we pass again A, V1, V2, matrix size. Then, as a result of that, in V2, we will have the result of the multiplication stored. And then we can say for int I equals 0, I being less than matrix size, I plus plus. We can just print the result vector. So percent point to f backslash n, and we want to have v2 I. And finally, we free the resources, so free A, free v1 and v2. And that should actually be it. So GCC matrix vector dash O matrix vector And let's see if we get the proper values. Yes, those are the correct results. So now we can also go ahead and change the matrix size to 40,000, and I can compile this, I can run this, but this will take some time, I think around 8 seconds, something like that. I hope this doesn't mess up the recording, but it shouldn't actually. But it takes some time, as you can see, to do the calculation. Then we get the output, and this is now what we're going to also implement in CUDA. And you're going to see why CUDA is so powerful for tasks like that. So I'm going to start here with a new file, matrixvector.cu. Here we're going to now just include stdio.h. We're going to define again a global void, which is going to be a matrix vector product. It takes again a float pointer to a matrix A, a float pointer to a vector v1, float pointer to a vector v2, and a matrix size integer. And now what we want to do again, remember we have the block index, we have the thread index. We want the individual threads to be responsible for parts of the calculation so that all of them can work at the same time in the GPU and deliver the result faster. And for this, we're going to say, okay, the row that I'm currently working at, the row that this particular function call is going to be working at will be determined by the block index, x, times the block dimension of x. I'm going to explain here in a second why we do this, plus thread index x. And this is now exactly the same thing that we had before. Remember, we had the same when I explained to you why we have the flattened array and why we have the matrix and why we go through I times matrix size. This is exactly the same thing. So we have I times matrix size here. So basically column size plus j. This is what we had multiple times in the last code. And this is the same pattern now. We take the row, the block index x, which is the row, and then we have the block dimension. I mean, actually, we're flipping this. I think it's actually the column. Doesn't matter. It works anyway because it's squared. But we have basically the block index x, the position, times how large is that dimension, this x dimension. So in this case, the matrix size, as you can see. And then we have the thread index in that row or column, whatever you want to think about here. And this is the j that we had before. So it's the same pattern. It's not different. And we're going to do the same thing now with the column. I think it should actually also work when you reverse it. I think so. But we're going to keep it like that because I don't want to mess up my prepared code here. Since it's squared, it doesn't actually matter. But we have row and column now, and we determine by the index of the block that we're currently at, and by the thread index, we determine what part of the calculation we're going to focus on. And to limit this, we're not going to actually use all of the threads. We're going to just say if the column that we're working at is 0 and the row that we're working at is less than the matrix size, because of course we can also go, we can also have, if we have, for example, a block size of 10, but we only have a matrix size of 8, we can go beyond the boundary. And in this case, of course, we don't want to go beyond the matrix to do calculations. So if that is the case, we're going to start with a float sum equal to 0 again. And we're going to iterate for this particular column that we're in. We're going to iterate through the rows. So I equals 0, I being less than the matrix size, I plus plus, and then we want to say sum plus equal. So the code is quite similar. Again, we have a row times matrix size plus I, and then I think my naming is kind of confusing. I'm not sure if I shouldn't reverse it. I'm gonna keep it like that, but maybe we're going to change it later on. V1 I, and basically the calculation is the same. We focus on one column or one row, and we go through the fields of that column, row, whatever you want to focus on here. and we do the multiplications there. And at the end, we have a sum, and this sum is what we set. And now here, row is definitely correct because we have in the vector rows, and here we want to say that this is the sum. So the calculation now is basically the same. The only difference is that we focus on specific, we don't have two loops here. We focus on a specific part of the matrix based on the block index and on the thread index. So every thread and block is going to have a different responsibility, which means that we don't have to do all of the work in one thread. We can split up the work, and different threads will produce different results in this vector in the GPU. That's the basic idea. And now we're going to take that and we're going to use that in the main function. Now, this is going to be a little bit trickier than before because there is something that we need to do here, which we didn't have to do before, which is we need to communicate between the device and the host. Now, the host is just my CPU, my basic program running on the computer here, and the device is the GPU. The device is this GPU, this parallel computing device, and we need to transfer information back and forth all the time to get the actual, to be able to pass values to the GPU and to get the results from the GPU to then display it on the host. That's the basic idea. So what we need to do is we need to define a float pointer A again, but we also need to define a float pointer A underscore GPU. And the same is true. We're going to do that now here in 3 separate rows, V1 and V1 GPU, V2 and V2 GPU. So we want to have the equivalent one time on the host and one time on the device. Then we're going to again define the matrix size. This is something we only need once, 40,000. Or actually, let's start with 3 first so that we can see again if this works properly. And then we're going to say dimension 3, which is a data type here, and we're going to define the block shape. Now, the block shape is the shape of the block itself. And basically, the block shape, let me again open up my favorite tool here. The block shape is if we have, again, this is the overall shape. So we have maybe 2 times 2 blocks. This whole thing here, this 2 times 2 structure will be the grid shape. This is what we're going to refer as the grid shape. In that grid shape, we have multiple blocks, 1, 2, 3, 4 blocks. And inside of those blocks, we have maybe a different shape, maybe something like this, 4 times 4 grid. This here is going to be the block shape. So the shape of the block itself. Just so that you don't confuse it. So the block shape is not the shape of the blocks, how they are aligned, but the shape of the blocks inside of the blocks. I hope this is not too confusing. And this is going to be, in our case, 32 times 32. In other words, in each block, we have 32 times 32 threads. That's what this basically says. And then we also have the grid shape. So how many blocks do we have? And this is important. We need to calculate this based on the matrix size. So we have 3 scenarios here. We have a matrix size that is perfectly compatible with the block size. So we have, for example, a size of 32, and we have a shape of 16. So we have basically, we need 2 times 2 to fill up the space, and it fits perfectly. Or we have something that's not precisely compatible. So maybe we have a matrix size of 30 and a block shape of 16. In this case, we would have to use still 2 by 2, but we have some remainder. And then we have also the case where the division would result in 0. And in this case, we would have to just force a 1. So if we have, for example, a matrix size of 10, and we have a block shape of 16 times 16. In this case, we would have 1 block, even though it's too much. So for this, I came up with this calculation here. Maximum of 1.0, so to force a minimum of 1, and then ceil float, actually like this, so typecasting float matrix size divided by float, and then block shape x. Yeah, that's it. So basically we're taking the matrix size, dividing it by the block shape to calculate how many blocks we need. We seal the number because we always want to have, you cannot have 5.6 blocks. In this case, you would need 6 blocks. And in the case we get a 0 out of this division, we go with 1.0 as a minimum value here that we force. And we can then basically just copy this. And the same thing is done with y for the y-axis. All right, so this is our grid shape. This is our block shape now. And what we do now is we allocate the space again. So this is basically the same as before. So I can actually copy this from our previous script that we just wrote, or not script, program that we just wrote. So this part is the same. We allocate a v1, v2 on the host, on the machine, and we also fill it up with the values here. So we're going to copy that. This is going to be the exact same thing. Yeah, just allocating locally and initializing again with 0, 1, 2, 3, and so on for the matrix and for the vector. Now, the new thing is we need to also allocate now on the device. This is allocating on the host, but we need to also allocate space for the GPU pointers here. And for that, we need to use a function called CUDA malloc. So CUDA malloc will, I'm going to use here a void pointer and a underscore GPU. This is going to allocate the size on, or the space on the GPU, on the device. And the size is the same, matrix size times size of float. And then we can copy this for v1, v2, and we need to remove a matrix size here because those are the vectors. But this is how you do that. So now we have space allocated for those variables. Now what we need to do is we need to take these, or actually just a and v1, because this is just an empty result vector, but we need to take the matrix and the vector that we want to use for the calculation, and we need to copy them to the device. So what we need to do after the allocation is we need to say CUDA memcopy, and we need to store in a GPU a. So we need to transfer a to the a GPU, and the size that we use for this is matrix size times size of float again. And we need to pass the keyword here, CUDA memcopy host to device. Same is done for v1. And that's basically it. We take the local matrix and vector from the host and we transmit it to the device, to the GPU. Then what we do is we perform the calculation on the GPU. Now we have all the data on the GPU. We perform the calculation on the GPU by calling matrix vector product. And here now, remember the angle brackets. We pass the grid shape and we pass the block shape. And then we call it on a underscore GPU, v1 GPU, and v2 GPU. We didn't transfer v2, but we still have v2 GPU and we still allocated it here. So the result is stored there. We also need to pass the matrix size. And then what we need to do is, since the result is now in v2 GPU, to get it on our system, on the host system, we need to transfer it back. So we do another CUDA memcopy, and we transfer from or into v2 from v2 GPU, matrix size times size of float. And here now we use CUDA memcopy device to host. And now all we need to do is we need to say for int I equals 0, I being less than matrix size I++. We print point to f backslash n v2 I. And that is basically it. What we need to do in the end, of course, is also free a... Oh, now I copied... What did I do now? Hopefully I didn't mess up anything. Free a, free v1, v2, and important, we also need to do CUDA free a GPU. And then the same thing with v1, v2. And then in the end, of course, return 0. That is basically it. So let me maybe recap again. We have this matrix vector product. We decide what we're going to focus on here. So which thread is going to do which part of the work. Here we allocate a GPU, v1 GPU, v2 GPU. So one variable here, or one pointer on the host system, one on the device system. Then we define a matrix size. We define a block shape. We calculate based on that the grid shape. We allocate on the host, we initialize on the host, we allocate on the device, we transmit to the device, we do the calculation, we transmit the result to the host, and we print it on the host, and we free all the resources that we allocated. Now let's see if that works, if we didn't mess up anything. So nvcc matrixvector.cu, and then matrixvector underscore CUDA, then /matrixvector underscore CUDA, and the results are correct. So let us go ahead now and change this to 40,000. And let's compile this, run this. And there you go. So now what we can do is we can time the two different versions. We can time the matrix vector, which is the C version, the core C version. And we can see that this takes around 7-8 seconds, something like that. 8.1 seconds. And if I go and say matrix vector CUDA, this one only takes 4.55 seconds. So it is a massive speed up. And this is a simple example. Now, I know it might be a little bit confusing to some of you who are not familiar with C or CUDA, but in the context of CUDA programming, this is a very, very simple example. This is not complex. But this type of parallel computing makes machine learning much faster because, again, as I mentioned, machine learning is a lot of linear algebra, matrix multiplications, matrix operations. And by focusing or by mapping the grid structure of the blocks and the threads to the grid structure of the matrix, you can do everything in parallel, and you can you have this new sort of paradigm of programming, and it makes everything much faster and much better. And this is now C. You can also do this with C++, and I think there's also an interface in Python. Maybe I will make a video about that once I get familiar with that. But this is how you do CUDA programming to speed up tasks, to speed up programs with parallel computing. So that's it for this video today. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and bye.